First thing we're going to do is run the application. This is done by navigating to the download, go into the main folder there, and then double-click the PIDtoolbox application. Once running, it's useful to pin the application to your taskbar for quick access, so you never have to return back to that folder. Once PTB is running, click on the green Open File button in the Control panel, then select the log files you wish to analyze. PTB opens in the Logviewer window. If you hover over any button, drop-down, or region of the window, various tooltips will appear to help. The Logviewer gives a sort of 30,000-foot view of the log file, displaying roll, pitch, and yaw axes in their entirety from the start to finish. At the bottom is the % throttle and % commanded motor output. On the left, you'll see the selection panel with a list of the parameters that you can plot. Simply click the checkbox of any parameter you wish to plot. You'll notice also there is a Y-scale input box where you can set the maximum scale in degrees per second. The first thing you're going to want to do is to trim the files, which sets the start and end points of a given file to be analyzed. All other tools will analyze only the data that are within these trim limits. To trim, we use the I and O keys on the keyboard, followed by the slider to position the desired time point. So for example, click I, then slide to the desired start or end time, then click O, and then slide to the desired end or out time. The slider may also be used to analyze specific time points in the log file. For example, if you move the slider to a specific time, notice down at the bottom right it shows the stick overlay at that time point, including the commanded motor outputs and current gyro reading. You can click on a panel to quickly expand an axis. Click again to return. To remain in an expanded view, click the R, P, or Y checkbox in the control panel on the right. To zoom further, click the plus magnifier in the upper right of the panel. It appears when you're hovering over a given panel. Then just simply click and hold the mouse button to select a region you wish to zoom into. You can use the slider here to examine any point of the zoomed view. There's also a handy period button that allows you to measure the period between any two time points. Simply click the button and then place the crosshairs over the first time point, then click the mouse, then move to the second time point and then click the mouse again. It displays the time in milliseconds and frequency in hertz between the 2 points. This is useful for measuring things like the frequency of an oscillation, for example. To clear all of these new lines and return to the normal view, simply click the file you wish to replot. Uncheck the expanded axis view by unchecking R, P, or Y if they are checked. This will return you to the original full view of all axes. Next to the period button is a handy markup button. Click the button, then move the crosshairs to where you want to mark. Click the left mouse button to draw, then the right mouse button to stop. To erase, simply replot by reselecting the file in the File drop-down. The next 4 panels are self-explanatory. There's line color, set font, line smoothing, and line width. The line smoothing only smooths the lines for viewing purposes. It does not change the actual data for downstream analyses. Below that are buttons for the Spectral Analyzer tool, the Step Response tool, the PID Slider Tool, the Filter Simulator, Test Signal Generator, and Setup Information tool. We will discuss all these separately. Then there's the Save Figure and Save Settings buttons, and a link to the official PTB website. At any point on any of the panels, you can click Save Figure, and it will save the entire output of whatever you have currently in view. Save Settings saves any of the settings that you wish to start in. Adjust things the way you want, and then simply click Save Settings. The Spectral Analyzer. If you click the Spectral Analyzer button, it opens this tool in a new window. At the top of its control panel is a list of the files loaded, followed by a list of the parameters available for analyses. You can select a maximum of 10 log files and 2 parameters to process at once. Default is the pre and post filter gyro. To plot the spectrum, simply click the green Run button. This plots the power spectral density on the roll, pitch, and yaw axes. The left panels show the full spectrum, and the right panels show the data zoomed in on the sub 100 Hz range. In this case, we see the dotted line is the pre-filter gyro and the solid line is the post-filter gyro after the filters have been applied. To see the current estimated filter delay, select Filter Delay from the Delay drop-down. Gyro and D-term filter delay are computed for each axis and displayed in the upper right of the right panels. Select the desired line smoothing using the smoothing drop-down. Similar to the Logviewer, you can zoom in on a given panel using the plus magnifier in the upper right of each panel, which is only visible when hovering over the panel. When you zoom, all the axes zoom at the same level. To return, you simply click the home link or click the reset button and the run button again. To open in an expanded view, click the R, P, or Y checkboxes. The PSD checkbox selects between the default power spectral density view and the traditional amplitude spectrum view. There's a handy markup tool here as well, and the Y-min and Y-max input boxes set the scale of the Y-axis. Below are the drop-downs to overlay where the RPM notches and dynamic notches were centered during the test flight. The color checkboxes select which motor RPM notch you wish to plot. When you click the RPM drop-down, you can select any combination of RPM notch harmonic you wish to plot. RPM is plotted in Hertz, that is, revolutions per second, and it's sorted, which produces a sort of sigmoid shape akin to a cumulative distribution, with each colored line representing each motor, solid, dashed, and dotted representing the first, second, and third motor harmonics respectively. The dynamic notch centers can be plotted in a similar way using the dynamic notch drop-down. For log files that do not have RPM data, motor RPM can be estimated using the RPM estimator checkbox. This is obviously not as accurate as real RPM, but it is estimated by adjusting the multiplier until the estimated RPM harmonic lines up with the expected motor noise seen in the spectrum. The first harmonic is usually the clearest to do this. Lastly, there is a handy motor noise tool. This tool tracks motor noise within each harmonic over time, selectively reading the noise at each motor RPM frequency and computing the average. If you select motor noise in the drop-down here, it plots the average motor noise for the first, second, and third motor harmonics, with the dotted line showing the motor noise before filtering and the solid after filtering. This is a very useful tool for comparing props, motors, or anything that impacts the magnitude of motor-related vibration. For log files that do not have RPM data, the RPM estimator can be used to estimate RPM, and then the motor noise tool can be used on that. Frequency by Throttle Heatmap. When you click the Frequency by Throttle button, it opens the tool in a new window. The Frequency by Throttle tool plots heat maps of the frequency of noise and vibration as a function of throttle. These plots are useful for analyzing motor noise patterns as motor output is increased. Go ahead and click the Run button to see how everything is organized. You should see a 4x3 matrix of heat maps with an overlay of the mean and peak output of each map. Along the top are 4 columns of drop-down. The upper drop-down selects the parameter you wish to plot. The lower selects the log file for that column. So you can plot and compare spectrograms simultaneously from 4 different log files, one for each column. Or if you select the file drop-down in the parameters box on the right, it sets all 4 columns with the same log file. And then you can compare across different parameters like pre versus post filtered gyro. The presets dropdown sets the 4 columns from left to right in various preset configurations. Alongside this is the markup tool as seen previously. Then there's the color map dropdown that sets the color map style, and there is a smoothing dropdown here as well. Below this is a checkbox for plotting 2D and a Power Spectral Density PSD checkbox to switch between the traditional amplitude spectrum and the power spectral density. Some may prefer the amplitude spectrum as it will be more comparable to the spectral output of Betaflight Blackbox Explorer. There's also a sub 100 Hz checkbox for each column. This zooms the heat map in on the 0 to 100 Hz range for analysis of commanded movement and vibration associated with things like prop wash. You'll see the zoomed heat maps with two horizontal yellow dashed lines denoting the frequency limits shown in the input boxes at the bottom right of the parameters. The peak and mean or average values overlay on the heat maps are calculated within these range limits and are intended to estimate things like prop wash. Changing the frequency limits changes the position of the yellow line overlay and the peak and mean values. You can modify and focus this to calculate averages and peaks within a specified range to facilitate more precise comparisons between, for example, different log files and different tests. The frequency by time heat map. When you click the frequency by time button, it opens this tool in a new window. At the top of the control panel is a drop down to select which file to plot. Below that is a drop down that selects which parameter to plot. Then there are the run and reset buttons, which function the same as other tools. Go ahead and select the file, then click run. You should see a heat map for roll, pitch, and yaw. In contrast to the frequency by throttle tool, here time is on the x-axis and frequency is on the y. To help orient you to what you are seeing, it's helpful to compare this to the % throttle motor panel in the Logviewer. Notice the similarity. As motor output goes up and down throughout the flight test, so do the bands in the frequency by time heat maps. Thus, those bands are motor harmonics. Bands that do not modulate with the motors represent resonance bands. So back to the control panel. Below the run and reset buttons are the save figure and save settings buttons like the other tools. Below that are smoothing parameters to facilitate viewing. The first smooths across frequency, and the second smooths across time. Next, we have a color map drop-down like before and a line width drop-down. This sets the line width of the harmonic overlay, which we will show in a minute. Next are R, P, and Y checkboxes, which expand an axis to full screen. There's a sub 100 Hz zoom that focuses the frequency by time heat map to a 0 to 100 Hz scale for analysis of things like prop wash or low frequency vibration over time. Like before, there's a markup tool and Z-scale input boxes that change the intensity of the color map. Below this are options to plot RPM and dynamic notch overlays, similar to what we saw in the main 2D Spectral Analyzer. But it's more intuitive here, as the RPM lines will fall right on top of the bands representing motor noise, with the solid line representing the first harmonic, dashed is the second, and dotted is the third. And the colors represent the motor number. Lastly, there is an RPM estimator and multiplier that functions like it did in the main 2D Spectral Analyzer. Step Response Tool. From the Logviewer window, you can click the Step Response button to open this tool in a new window. At the top of the control panel here is a list of log files available to plot. You can plot up to 10 log files at the same time. Select a set of files, then click Run. From left to right, we see the step response traces, the PID and feed forward values for each line, the mean peak response and latency plots with error bars. If the files are not systematically organized, you can organize the color by plotting the files one at a time. Simply select a file, click the Run button, and repeat this for each log file in the desired order. This can be useful so you can organize the results systematically with the PID changes. For example, here they are organized with systematically increasing D term. Below the Run button is the familiar Save Figure and Save Settings buttons, which are self-explanatory and described earlier. Below that is a period button that works the same as it does in the Logviewer. Simply click period, place the crosshair at the first location of interest, click the mouse, then move to a new location, then click again. It shows the period between two time points in milliseconds and the frequency in hertz. This is useful for measuring the frequency of an oscillation, which is important for determining whether it is due to a noise source or from excessive PID gains. Below this are two drop-downs, a smoothing drop-down, which is intended for firmwares like FETtech that filter less on the gyro to help facilitate step response clarity. Next to this is a latency selection drop-down. This selects between two different ways of measuring latency. SR latency refers to step response latency, which extracts a latency metric directly from the step response curves themselves, essentially the time that the curve first passes the 0.5 point. The X-core latency measures the cross-correlation lag between the set point and the gyro raw data, which does not generate error bars. I use both to facilitate decision-making on how high to set the master multiplier PID gains. In essence, one can corroborate the other in case there's variability between tests, and this can help in making a better decision about whether there's any value in pushing the master multiplier at higher and higher points. Next are the checkboxes to plot R, P, or Y, or any combination. Then there is a plot expand checkbox that makes the plot go full screen, and a raw checkbox that plots the individual step response traces that go into the average trace. This is useful for seeing the variability in the result, which is affected by various things like a noisy gyro, poor or inadequate input data, undertuning, and various other factors. Below this is a drop-down to select between whether you want to plot peak and latency panels or a handy Betaflight slider view. The sliders only show changes between the tests as colors that correspond to the test log, and the non-changes as gray symbols. The PID Slider Tool. If you click the PID Slider Tool button, it opens this tool in a new window. This slider tool may be used for firmwares that do not have a PID slider system. This allows you to follow the PTB basement tuning method, maintaining the ratios between PID terms and axes as you optimize the PIDs. There's a drop-down that sets the PID start values for various firmwares, including Betaflight for pre-slider versions, iNav, FETtech, KISS Ultra, and Quicksilver. When you select a firmware, it shows the start values on the left, which can be changed manually as desired, which might be necessary if the base tune is already very far from the optimal. On the right are the test values, that is, the values you will plug into the firmware that you're running. As you move the sliders, you change those test values. The PD ratio only changes the D term, as is needed for optimizing the P to D balance. Then there's the PI slider, a roll pitch ratio slider, a yaw slider, and a master multiplier that works exactly like in Betaflight. The sliders overall do not match Betaflight exactly, but they're instead designed around the key ratios that define the PTB PID tuning method. The Filter Simulator. If you click the Filter Sim button, it opens this tool in a new window. At first glance, there's a lot going on here. This tool is useful for gaining a deeper understanding of the filters used by firmwares like Betaflight. The left panels describe low-pass filters, and the right panels describe notch filters like Betaflight RPM filters, static notches, and dynamic notches. The sliders at the top set the cutoff frequencies. The plots from top to bottom show filter attenuation curves, followed by filter delay curves, phase delay curves, and filter step response curves. This is an advanced tool for those who want to build their knowledge of real-time filters over time. I will not go into detail here about everything this tool has to offer, because I have posted earlier videos describing key features about this tool and have made some detailed discussions about it in the PTB Patreon Q&A video content. For now, just play around and try to become familiar with what's going on. Again, I consider this a very advanced tool specifically designed for people who are already experienced in PID and filter tuning, but want to build their knowledge base in our constantly evolving hobby. The Setup Information page. If you click the Setup Information button, it opens a new window with all the details about the selected log files. There are 2 columns of information with the drop-down to select 2 different log files to compare. Differences between the log files are highlighted in red. If you click the Show Differences Only checkbox at the top, it shows only the parameters that are different between the log files. This is very useful for tracking changes from test to test and between different log files. There is a link to the PTB official website. There you'll find links to my PID tuning consultation service for those who would like direct one-on-one help over scheduled Zoom video meetings.